So let me tell you what game theory is. It's a subfield of economics. Specifically, it's the study of strategic decision making. When I say strategic, I'm specifically thinking competitive, in the idea that your decisions affect your opponent's payoff, his decisions affect you. Most of the time in game theory, you're trying to find what's called a Nash equilibrium. Let me tell you what that is. A Nash equilibrium is an equilibrium that's a stable situation in which no one would change their strategy with knowledge of their opponent's strategy. Basically, both people have a certain expectation. You expect your opponent's strategy to be something, it's true. They expect your strategy to be something, it's true, and neither one of you want to change your strategies. It's stable in that sense. So now let's move this to baseball, talk about what makes an effective fastball. Last year, according to Fangraphs, R.A. Dickey was number 2 out of 88 qualifying starting pitchers in fastball effectiveness. Pretty interesting because he throws pretty slow. 83 miles an hour, slowest of all 88 starting pitchers. He was number 2 in effectiveness. Contrast that with someone like Justin Verlander. He was 16th in effectiveness, pretty good. Obviously throws very fast, number 3 in velocity. Might seem like I'm cherry picking data here, actually. I'm not. There's only a 0.06 correlation in between effectiveness on a fastball and velocity. If you've read anything I've written about this, you'd probably be surprised that I'm saying that. Velocity is important. Let's talk about why. R.A. Dickey throws fastballs 15% of the time. Justin Verlander throws fastballs 44% of the time. Basically, it's all about expectations. What it comes down to is the pitchers that have the most effective fastballs because they're fast can throw them more often because the hitter needs to look for them, gets on them quicker. As a result, they have less time to react in general. It compromises the hitter's effectiveness on other pitches. So basically, that's what happens. The correlation between how fast a pitcher throws and how frequently he throws his fastball is 0.41. It's a really high correlation for data like this. But it comes out of the fact that if you have a fast fastball, you can become more effective by throwing it more often, making the hitter expect it. They do less well on the fastball itself. It makes the rest of your pitches important. R.A. Dickey's fastball, therefore, is effective specifically because it comes as a surprise to hitters who know 85% of the time it's not coming. There were a couple of previous studies that really formed my thinking on this and helped me approach it a certain way. One of them was by Sky Andrzejczyk at Baseball Analyst in 2010. He looked at hitters. He tried to look for the correlation year to year in between how a given hitter would do against certain pitches. So Ryan Howard against a slider year to year, how well does that correlation hold up? And the correlation is almost non-existent. And basically what it comes down to is expectation. For a guy like Ryan Howard, he's almost dead league average against sliders for his career, 0.01 runs versus average per 100 pitches. Now, if you ever see Ryan Howard try to hit a slider, that might surprise you a little bit. What happens is that pitchers throw him sliders all the time. He's got to look for them all the time. He sees sliders 21% of the time. That includes pitchers that don't even throw sliders. The guys who do throw sliders throw them so much that he still sees 21% sliders. As a result, he's looking for it all the time. It compromises his fastball effectiveness and makes it so that he's not so bad against sliders. It makes him worse against fastballs. There was another previous study that really helped me thinking about this. It was by Kenneth Kabash and Stephen Levitt, a couple of economists, who looked at the payoffs against fastballs and non-fastballs and reasoned correctly that they should be very similar if pitchers are playing the correct strategy. The idea being that if there is a count, they control for count and a lot of other factors, if you control for count and all the other factors, and there's a situation where the pitcher can get a higher payoff by throwing a fastball or a non-fastball, they should just be throwing it all the time. Across all counts, they randomize. They do some pitches sometimes, some pitches some other times. And as a result, they should come out equal. They found that they don't quite come out equal, that fastballs were thrown too often, the payoffs on them were lower. I'm going to get a slightly different result. I think that the main reason that they found this was that they used OPS, which is a good metric, but it does underrate the importance of walks and therefore overrates the importance of non-fastballs, which can end up out of the strike zone a lot more. So what I'm going to do now is I'm going to give you 3 basic counts, 3-0 counts, 3-2 counts, and 2-2 counts, and try to build up the model of just how we would use Nash equilibrium in game theory to think about approaching a given count. And then we'll be able to take this to data. So I'm going to start with a really simple example, 3-0 pitches. and ask a question that probably most people in here know the answer to, which is, why is it that batters swing at just 8% of 3-0 pitches? This example will motivate the model and allow us to think about things that are more complicated. So what we do is we put the pitcher and batters in a table, and we basically have their payoffs in the cell, which I'll fill in a minute. The pitcher is what's called the row player. He chooses whether to throw strikes, and chooses either the strike row or the ball row. The batter is choosing what the column, he's the column player, choosing swing or take. And what we'll do is we'll think about what are the payoffs in these cells. Now, the way it works is the pitcher's payoff will be on the left, followed by a comma, followed by the batter's payoff, but since the pitcher's payoff is always the negative of the batter's payoff, we'll talk about it from the batter's perspective. So the best case scenario for the batter is ball take, because he gets a short walk for it. The worst case for the batter is taking a swing at a ball out of the strike zone. So we'll give him 4 points, utils, whatever, for ball take and 1 for ball swing. However, between strike swing and strike take, if you look at the data, batters actually do better in 3-1 counts than upon making contact in a 3-0 count, because they still get walked a lot in 3-1 counts and they still get good pitches to hit a lot of the time in 3-1 counts. So if we were going to rank the cells from the batter perspective, the most, second most, third most, fourth most, and so 4, 3, 2, 1 will be the payoffs, negative for the pitchers. Now we want to talk about how to solve this game. So remember what Nash equilibrium is. A Nash equilibrium is controlling for the other person's strategy. You best respond, they best respond to you, and you both expect each other's strategies. There's one cell that'll solve this here. If we look from the pitcher's perspective and say, suppose he expects and knows the batter's going to swing, what's he going to do? Well, he would get a payoff of -1 if he throws a ball, -2 if he throws a strike, so he'll throw a ball. If the batter is definitely going to take, though, obviously he wants to throw a strike, because -3 is better than -4. So those are his payoffs. Those are his best responses. Now, let's think about the batter's perspective. Obviously, if it's a ball, the batter's not going to want to swing, so he's going to take 4 is bigger than 1. But if it's a strike, he still would rather take 3 is bigger than 2. Those are his expected payoffs. Put those together, and there's only one cell where they're both best responding to each other. They're both unwilling, they both don't regret their strategies, conditional on what's happened, and that's this cell. So let's complicate this a little bit more, and we'll talk about full counts. Full counts are going to be different in a few ways. So the way that I filled in the payoffs to this table is, rather than get the actual numbers, again, I just kind of rank them. So I call 1 if it's good for the player, -1 if it's bad for the player. So if it's a full count and ball take, obviously that's a walk. That's bad for the pitcher, good for the hitter. So the pitcher gets a -1, the hitter gets a +1. Obviously, taking strike 3 works the other way. That's why the pitcher gets +1, batter gets -1. In terms of if it's a swing, then on average, the batter is definitely going to be better off if it was a strike, so we'll give him +1 there, and we'll give the pitcher +1 there. Here are the best responses. There's actually no situation here where somebody doesn't regret their decision. Suppose that it's strike swing. In this point, the pitcher definitely regrets his decision. He wishes that he threw a ball in response to swing. Of course, if the batter is swinging, then the pitcher wishes that he threw a ball. I'm sorry, he wishes he threw a ball. If the pitcher is throwing a ball, the batter wishes he took. If the batter took, the pitcher obviously wishes that he threw strikes 3, and obviously then the batter would wish that he swung. So there's no dominant strategies here. There's no pure strategy equilibrium here. Someone always regrets their decision. In game theory, the way we solve this is what's called a mixed strategy, which is you don't do one thing all the time. You randomize. In a situation, you have a certain probability of throwing a pitch in a given count. So the math works out here with these made-up payoffs that half the time the pitcher's going to want to throw a strike, half the time he's going to want to throw a ball, and half the time the batter's going to want to swing, and half the time take, and nobody regrets their decision to follow the 50-50 strategy. So now let's talk about 2-2 counts and what's going to be different. Well, obviously taking strike 3 is going to be the same. If you swing, you hit the ball in play, whatever happens, doesn't matter what the count is, or you're going to end up, whiffing, same. The real difference comes for ball take, which is that you end up in a 3-2 count instead of a definite walk. So when you think about 2-2 counts, there's one cell that's really different. And that's going to affect the strategies. So let's think about how this works. From the pitcher's perspective, all of a sudden, if the batter was doing the same thing, he would suddenly have this really high payoff to ball take, so he would want to throw more balls. Of course, if the pitcher is throwing more balls, the batter's going to want to take more. The Nash equilibrium works out that the pitcher throws now 33% strikes instead of 50, and the batter swings now 33% out of 50. Obviously, that's not surprising for the pitcher. The batter is actually pickier in a 2-2 count than a 3-2 count. Now, when I put together my articles about this at Hardball Times, I said that it seems like the mantra is that, when the hitter's back in the count with 2 strikes, he's really got to, just expand the zone and swing when he's got to swing at 3-2 count. He can think about a walk. So I was thinking this might be evidence of some irrationality on the part of batters, but it turns out batters seem to be following this strategy, mantra or not. Like we said, the pitchers are more likely to throw a strike in a 3-2 count than a 2-2 count. The hitter is more likely to swing, too. You might say, well, what about location? Maybe he's swinging more because the ball's in the strike zone more. But even if you factor in location, the batter is a little bit more likely to swing, 91% versus 80%, if the ball's in the strike zone with a 3-2 count. And a little bit more likely if the ball's not in the strike zone to swing in a 3-2 count than a 2-2 count. The idea being that he rationally expects what the pitcher is likely to do and factors that in. Now, if you notice, I kind of changed the rules here. Because in the previous tables, what I was doing was I was saying, well, if the batter decides to swing or take, there's no response here. Right now, I've added this extra wrinkle, which is that the batter has a second to observe the pitch, see what he thinks it is, and react accordingly. So what we're going to have him do, and this is why it's called Bayes at the plate, is we're going to have him do Bayesian updating. He's going to have a certain belief of what pitch the pitcher's, how likely he is to throw a fastball or not, and based on what he sees, react accordingly. So we're going to do this in a game tree. A game tree is going to look like this. We're going to have a 3-2 count again. We're going to have the pitcher deciding whether to throw a fastball in the strike zone or a changeup out of the strike zone. The pitcher, we're going to call him Chuck because he's chucking the ball. And then we want to add in an extra step. If we were doing a regular game tree where everybody knew everything, we would have little branches after fastball of what the batter could choose to swing or not swing. But there's something else that happens, which is the batter makes this observation. His observation might not be accurate. So we call this the agent nature, who's not a person, just a separate entity that reacts and behaves next. They're the next actor. And they send a certain signal that it's a fastball with probability X if it's actually a fastball. But unfortunately for the hitter, they send a wrong signal with probability Y that it's a fastball even if it's not. Which means, from the batter's perspective, he doesn't know whether a fastball was thrown. If he sees a signal, he says either that's a fastball where I'm getting the fastball signal, or it's a changeup where I've mistakenly gotten the fastball signal. That's decision node 2 for him. Decision node 3 is no signal, factoring in maybe it's a fastball that I got the wrong signal and maybe it's a changeup. So the batter's going to have to behave like a Bayesian here. He's going to have to think about what was the pitcher's likelihood of throwing a fastball in the first place, and then what are the probabilities of the signals. So because he's behaving like a Bayesian, I've decided to call him Willie Bayes. So there's his specific I like that. And then what the batter's going to do, he's going to factor these in, decide whether to swing or not swing, conditional on the signal he receives, factoring in both the original probability that he thinks the pitcher is going to throw a fastball and the probability that nature acts a certain way. And these are going to be the same payoffs from the 3-2 count. Looks like it's kind of complicated to solve, but there's only one way that it actually works. And that is when the batter chooses to swing when he gets the signal of fastball that's in the strike zone, and not swing when he gets the signal that's a changeup out of the strike zone. The reason actually makes sense when you think about what Nash equilibrium means, which is that if he was not swinging when he had signal of fastball, that would mean his prior belief of how likely the pitcher was to throw a fastball was very low. So even when he gets the signal, he says, it was still probably a changeup. But guess what? If the batter's never swinging, the pitcher's always going to want to throw a fastball, so that wouldn't rationally expect what the pitcher's going to do. Same thing works the other way. If he's swinging even when he gets a signal of changeup, it's because he thinks that the pitcher's very likely to throw a fastball. But if he's swinging everything, the pitcher's going to want to throw a changeup. Basically, the pitcher is going to throw just enough fastballs to keep the batter following this strategy. And that's the only stable Nash equilibrium, what's called a Bayesian Nash equilibrium, because they're incorporating Bayesian probabilities. So if we take this now and start talking about 2-2 counts, the same things are going to play in, which is that all of a sudden the pitcher has a little bit lower cost to throwing a ball, so the pitcher's going to throw fewer strikes and the batter's going to swing less in response. You can do this type of analysis through all the counts and work it out. 3-1 counts kind of work the opposite, which is that now it's the batter that has this low cost to taking strikes. What that means is that the pitcher would need to throw more strikes to entice him to swing in a 3-1 count versus a 3-2 count. Carrying it straight through, the closer you get to a strikeout, the more strikes there are, the batter's always going to want to swing more. Now he's got a higher cost of taking strikes, especially with 2 of them. And the pitcher's going to throw fewer strikes because of that, because there's lower risk of a walk, because he's more likely to end up with a strikeout, and because especially with 2 strikes, there's this really high payoff to getting a whiff. From getting closer to a walk as balls are added over the course of a plate appearance, the pitcher's going to throw more strikes because now there's a really high cost to him of the batter taking. But the batter situation is a little trickier. Kind of depends on the count. On one hand, he might get less picky because the pitcher is throwing more strikes. On the other hand, he might get more picky because suddenly, especially with 3 balls, the benefit of taking a walk gets really exciting to him. Players actually approximate these strategies. If you look at this table right here, in terms of how often the pitcher throws a pitch in the strike zone, you see more strikes, he throws it less often in the strike zone. More balls, he'll start throwing it more often. Batter is pretty good at this too. These are swings for balls in the strike zone and out of the strike zone by count. You can see as strikes are added for a given number of balls, he swings more, both at pitches in and out of the strike zone than he did. And as balls are added, he starts to factor in the pitcher's strategy with 1 or 2 balls, swinging a little more. But then 3 balls, he suddenly has a really high payoff to a walk, so he's more likely to take. So I say approximate these strategies. The question is, how carefully do pitchers and hitters really follow these strategies? And what I'm going to do is I'm going to loosen the definition using data to just fastballs versus non-fastballs, lump them in using PitchFX data, which I got from Jeff Zimmerman, who was very helpful with this. And basically the way I'm thinking of this is the same way I had the fastball and changeup. Fastball is more like a strike. It's easier to hit, but easier to control. Basically, pitchers should be throwing enough fastballs because of the Bayesian-Nash equilibrium we found before. The batters are enticed to swing sometimes, but enough non-fastballs that they're discouraged. And just like that Kavash-Levitt paper, the payoffs to fastballs and non-fastballs by count should be equal, at least if you control for everything. The question is it? Not really. This is using that data, using runs per 100 pitches thrown through the rest of the plate appearance. The reason I did through the rest of the plate appearance is because we need to factor in what happens after the 3-0 fastball down the middle, and say not just it's any 3-1 count. What's a 3-1 count that follows that? So this will get a really unbiased result. The numbers in these tables, the bigger numbers, are fastball runs minus non-fastball runs in the account. What that means is that positive number would mean more fastball runs than non-fastball runs, which would mean that the batter's doing much better when a fastball is thrown, and the pitcher should be throwing non-fastballs more. Negative numbers work the opposite way. The pitcher's throwing too many. And although these numbers are small, they're actually statistically significant in many cases. You see that in general, fastballs are underused with no strikes and overused with 2 strikes. With 2 strikes, batters are really antsy. They tend to swing on a lot of pitches, even ones out of the strike zone, more than they should. And pitchers aren't taking advantage of this enough. This table up here does not control for the hitter quality. I did look at that a few different ways. It didn't really change results much. It kind of took like 0-0 counts, maybe 1-0 counts down a little bit. But you still get the pitcher's behind in the count. He's not throwing enough fastballs. Pitcher's ahead in the count. He's throwing too many fastballs. And so that's basically, the batter's swinging too much with 2 strikes, especially 2-0, 3-0 counts, 2 fastballs. Pitchers should know this and capitalize. So there's your answer. But why haven't they figured this out? Sounds like a little bit of a silly question. But it's not. People actually kind of do math in their head all the time without really knowing it. They're not actually solving the math, they're just behaving as though they do. And so when economists say people are rational, people tend to dismiss that. It's more that people kind of learn over time, learn by doing, copy each other, etc. Great example is pool players. Pool players are hitting the ball at a very specific angle and a very specific speed. Now, that's actually solving a very complicated differential equation, but I don't see pool players up there doing differential equations on graph paper. What they're doing is they're just learning over time, figuring out just about how often it works, getting better at it, and solving. The same thing works when businesses price things. They're not doing optimization calculus a lot of the time, but they learn that, hey, if we charge a markup of 30%, then the businesses that have done this, or when we've tried this in the past, we just can't sell enough units. And when we try to just sell a markup of 10%, we don't even make back our overheads, and 20% seems to be in the middle, and they end up working towards that. So that explains why it doesn't work in baseball, was that it's a rare skill. I can do all the math, but I can't throw the 95-mile-an-hour fastball. So I can say, hey, I think that they should be throwing 55% fastballs. They're only throwing 50% fastballs, but that doesn't mean I can go up there and do it. You can get away with it if not that many people can copy and replace you. The way that the rationality works in the real world a lot of the time is that people copy each other, learn over time. Imagine that with pitchers with very different skill sets. All right, Dickey throwing 44% fastballs like he's Justin Verlander. I don't think he's winning the Cy Young. So to bring this to data, using this logic that it comes down to rare skills, I broke pitchers down into ones who threw certain common pitches the most often. So I found the 10 starting pitchers that threw changeups the most, sinkers the most, sliders the most, curveballs the most. Try to see how their behaviors were different from other pitchers with these specialized secondary pitches. And they do behave differently. The question is really, are they adjusting strategically? Here's a clue into why I think that this rare skill thing is really what's motivating this. The guys with the least specialized secondary pitches, the 50 or so guys that were not included in these specialized pitches, their table actually looked much better. They were being much more rational because they were behaving with a similar skill set as a bunch of other pitchers and had kind of copied over time how often we throw a fastball in a 2-0 count and a 1-2 count, etc. And had learned. But these specialists with these rare skills can kind of get away with it. So I'm going to go down the 4 main pitches right now and talk about some of my findings there. Changeup pitchers. These are guys like Cole Hamels, Mark Burley, and the 8 other guys who threw changeups the most. I'm going to go through the differences in their skills, the differences in their behavior, and then some of the differences in outcomes. Differences in skills. Comes down to what happens on their non-fastballs. They're usually changeups. They're weaker hit on balls in play. They're also whiffed at more. And they're also thrown out of the strike zone. When it comes to behavior, a major difference is that they throw way fewer fastballs in 2-strike counts than other pitchers. So that might surprise you if you saw the articles at Hardball Times where I talked about if hitters were behaving rationally, then a pitcher's going to need to throw, a good changeup pitcher's going to need to throw more fastballs in those counts to entice the batter to swing it all. But we learned before batters aren't behaving all that rationally. They seem to be extra antsy with 2 strikes. So it turns out changeup pitchers are throwing fewer fastballs with 2 strikes. They should be taking it even further than that. Their changeups do even better with 2 strikes versus other pitchers' non-fastballs. And the batters just swing too much, and they should be trying to get away with this. The lesson here, let me take one more thing. There are fewer fastballs thrown in 1-0 counts, and especially 2-0 counts by changeup pitchers as well. But they actually do better on fastballs in those counts. Here's what's happening. Batters know when a changeup pitcher's on the mound that this is a guy who's a specialist in throwing a pitch that really looks like a fastball. But it's not that, it's really tough to tell. So in a 2-0 count, when they can afford to, hitters take fastballs from these guys a lot, which means that they can sneak in a strike and even up the count a lot easier because of the suspicious batters. But they don't. The lesson here really is to know thy skill set. If the market's not going to learn if it can't adjust. If there's no ability to replace changeup pitchers and figure out if I was Cole Hamels, how often I would do it, but I don't have a changeup like him, it doesn't matter. Now let's talk about sinker ball pitchers. These are guys like Tim Hudson, Justin Masterson. Now because of the way I was using the data, I counted sinkers as fastballs, just lumping and sinking fastballs and 2-seamers and all that. The idea being that when I say a pitcher here throws too many fastballs or something like that, I'm specifically saying too many fastballs and sinkers combined versus other pitches. Differences in skills for them are actually very predictable. Their fastballs, which are sinkers, in play tend to be hit weaker, but their non-fastballs are not especially good pitches for them compared to other pitchers, and so they do worse on them. They're also ground ball pitchers. That's how they get their outs. So the strikeout is less of a factor in their plate appearances. In terms of behavior, these guys do throw more fastballs, so they got the good sinkers. They throw those more often than other pitchers. But they kind of do this consistently about 5% more across counts, and that's not actually smart. Batters have a certain behavior difference too, which is very rational. They take more fastballs because they can't hit them as hard. They end up hitting ground balls a lot of the time. And fewer non-fastballs than they do versus other pitchers. Makes sense. They get worse outcomes. In terms of outcome differences from the sinker ball perspective, they're doing similar things. They still underrate non-fastballs with 2-strike counts. but especially with zero strikes, and especially get to like a 2-0 count, fastballs really do better in these counts, but they're still throwing a certain percentage of non-fastballs, and they should be really dropping it. They should be really coming in with the sinkers in a 2-0 count. And it's a similar reason. When behind in the count, the hitter knows just because I see this sinker, that doesn't mean that I should really swing at it, because I'm a little bit more likely to hit ground out or run into a double play or whatever than versus other pitchers. So that makes the sinker ball pitchers able to afford a fastball a little bit better, and the batters are less inclined to swing at them. But they don't. It's an area where they could improve. Getting a lesson knowing their skill set. Next, slider pitchers. These are guys like CC Sabathia, Ryan Dempster. These guys are really power pitchers. Real differences in skills, they really miss bats a lot, especially when they throw those sliders out of the zone. The downside for slider pitchers, at least for these 10 guys that I looked at, are that the balls in play tend to be hit a bit harder. In terms of behavior, batters really just swing more at non-fastballs out of the zone, really giving the slider pitchers a really ability to capitalize with those pitches. But the slider pitchers kind of pitch backwards more. They actually throw more fastballs than other pitchers when they're ahead in the count and in a 2-strike count, and fewer fastballs when they're behind in the count in those 2-0 counts and things like that. That's not what I recommended, and it doesn't end up working out for them very well. Basically, they do even worse than other starters on non-fastballs and 0-strike counts, and even worse on fastballs and 2-strike counts. And this is pretty amazing, because they actually do very well overall on 2-strike counts, but it comes from the times that they do decide to throw the sliders that hitters swing at all the time. The prescription here is really just throw a lot more sliders in 2-strike counts. Batters can't tell them from fastballs, just like changeups, and they're forced to swing more with 2 strikes. They don't. When slider pitchers get ahead in the count, they have the same feature that the changeup pitcher does. They can afford to have the batter take, the batter's likely to take strike 1 in like a 2-0 count or 3-1 count, or 3-0 count, and they can afford to throw more fastballs in this count. They're not doing it, even as much as other pitchers. Last, I'll talk about curveball pitchers, guys like Adam Wainwright and some Volquez are on this list. They really are a very different animal than some of these other pitchers. I'll talk about that. In terms of relative skills versus average starting pitchers, they're really similar though. Their contact rate's pretty similar, their rate of pitches in the strike zone is similar, their outcomes on balls in play are similar, but their behavior is different. They throw fewer fastballs overall, especially when they're ahead in the count. And batters are really picky against them. Both fastballs and non-fastballs, they swing a lot less. The result of throwing the same amount of pitches in the zone and the batters taking more pitches, they end up with more walks and then end up leading to more runs. Where curveball pitchers really make a big mistake, I noticed, is 2-0 counts. They throw a lot of non-fastballs. They throw these curveballs in these 2-0 counts. And batters don't swing at them. And that's because the batters kind of know what a curveball is when they see it. It's a little bit easier to detect. It's more difficulty in figuring the trajectory of the curveball, whether it's going in and out of the strike zone, rather than knowing whether it's a curveball or not. Similarly, the curveball pitchers really had poor performance on fastballs and 2-strike counts because the batters are swinging at the curveballs a lot. So I think it's a very different kind of Bayesian updating here. They're kind of Bayesian updating what's the probability of a strike maybe versus what's the probability of a curveball versus a fastball versus what I'm seeing. You can detect that quicker. I also think that at least for the 10 guys that I was looking at, they had not especially good fastballs maybe in the league because of their bonus, whatever. So if I were to change the game now, the Bayesian updating game, and figure out how the batters and pitchers respond to each other, the features I want to pick up are that the curveball is easily discernible from the fastball, but it's hard to tell where it's going. So it would look maybe something like this. The idea being that the batter is getting 4 signals instead of 2. Instead of the fastball signal versus changeup signal, being fastball, strike, fastball, ball, curveball, strike, curveball, ball. And it's really a question of figuring out whether it's a strike or a ball given the pitch is thrown. You don't need to worry about the payoffs as much. The payoffs there are from tables that I was putting together on these pitchers. But the solution is going to come out the same, which is that they better be equalizing their payoffs for each of their decisions. Because if that's not working out, then they have a pure strategy they should be following, they should be throwing all the time. So let's talk about where to go from here. The first lesson is to know your skill set. If you have a specialized pitch, copying other pitchers isn't going to work, and there's a real advantage to knowing how that's going to affect payoffs and behaviors in the batter reaction accordingly. Across the board almost, and especially for the specialized guys, the pitchers should be throwing more fastballs when they're behind in the count. The batters take those pitches a lot. They should be throwing more non-fastballs when they're ahead of the count. The batters are swinging at those way too much. The batter's strategy really, just be a little bit more skeptical with 2 strikes. They clearly should be willing to strike out sometimes to work the count, given how infrequently strikes are thrown in these count that they're not really factoring that in. I think there's a few different ways you could apply this and really take it a lot further, which is learning what the hitters know when, talking to them, figuring out how to build the model differently to certain types of pitchers. Curveballs all look alike, that these guys should be grouped, and look at these tables, specialize. If you group them better, maybe expand the data. I only looked at 2012, expanded over a few seasons. I think you take it farther. And I think surveying hitters to understand their decision making, you could move that into the same Bayesian framework in other ways and do a lot further. So thanks. I'm happy to answer any questions.
Let's say someone moves from a non-optimal to an optimal list of pitches. What's the overall size of the effect on that?
I mean, it's tough to know exactly, because then you need to factor in how batters adjust. If batters are, doing what they're doing, it seems like in a lot of those situations it's about one run per 100 pitches in a given count, certain counts. So I mean, that's going to add up over time, certainly. Yeah, that would probably be a good estimate. Yep.
Have you looked at pitchers throughout their career and whether they get more optimal as they get further into their career? Perhaps there's a Bayesian prior of how they should be pitching and they're updating it as they go along.
I love that idea. No, I didn't. I only looked at 2012, but that's a thank you.
That was my question as well, was you're basing this upon the idea that they learn by watching each other, and was there a difference of difference?
Yeah.
For your average swing rates by count, were those normalized for the same types of batter groups?
I didn't normalize for the batter groups on that stuff. I normalized for some of the absolute run differences. The magnitudes there were pretty big. It's a good idea to look into stuff like that. Yeah. Yeah.
Would this be different if there was a cost to the pitcher associated with each pitch? If he's on a pitch count, he doesn't want to waste pitches. He wants to get as many games as possible, but he's only going 100 pitches, 110 pitches.
Yeah. I mean, I guess you'd move towards contact.
Pardon?
I guess you'd move towards contact, so you need to factor that in. How many runs? I mean, you need to factor in that cost and put that in there too. But you could do that. It's probably easier than incorporating the hitter type, which I was trying to do. I mean, you figure out what's your cost function, and you just add that in. Yeah?
How are you quantifying quality of contact?
Just linear weights on balls and fly. I use straight up linear weights, which is why I got a little bit different results than the Kabash-Leva paper, which will get into.
Did you look at game situation at all in terms of first inning 3-2 count or
I didn't. That's on my list of things I think I do. I'm trying to expand the sample size as much as I could within 2012 right now. That was what I was doing here, but that is a good idea.
If his team's up by a lot, then he probably just throws strikes and doesn't care if he gives him one home run or whatever.
Yeah, that's definitely where pitching to the score would be a real thing back then. Yeah.
This seems kind of like ready to go, and sort of, if you could just talk to some batters and pitchers, it would be somewhat easy to, to have them follow this. Have you thought about maybe getting with some minor leaguers or something who don't stay perhaps as set in their ways, and might be this could be some benefit to them. They don't have the innate knowledge for the ones that are kind of doing this.
I think it would probably be much more malleable. I don't know any, so someone should tell us.
I can only imagine a team letting you fool with their minor leaguers, with them.
Yeah?
You suggested surveying the hitters and trying to understand how they think of what count and stuff. Do you ever see usually that simulator in which they can practice these skills? You talk about repetitiveness, and you can only be in the box so many times and get so many at bats, but do you see some sort of simulator in which they can kind of work their mental game as well?
Yeah, I think that could be the type of thing if they're, put them in the cage and say, okay, it's a 2-2 count, and this type of pitcher's on the mound. What do you react accordingly? I mean, you kind of need a lot of it's very innate, so it's a little bit, about just tweaking things a little bit. But yeah, I think that making them practice it more, I think you could get them used to figuring out how to optimize. Yeah. Yeah?
Based on the fact that there are 4 balls and 3 strikes, should pitchers be throwing the ball outside of the strike zone more often in general?
It seems like with 2 strikes, yeah. With no strikes, no. I think I would say. Question?
I've got one more question.
Okay.
Well, it's clear that both pitchers and batters can make these adjustments. If one was to try and make these adjustments, you couldn't assume that the other side would counterbalance by making their adjustments as well. Therefore, you've got slightly
It's a
different
moving target,
situation.
absolutely.
So,
I bet that people learn over time, and I bet that, with some of the, here's, like the Bloomberg stuff from yesterday, like, this pitcher's always throwing this in a certain count. There's probably some element of adjusting that's already going on. So those are conditional on the way things are right now, averages. But yeah, it is absolutely a moving target, and that's the whole point of thinking about it from the Nash perspective. All right, thanks everybody.